Gelfand-Tsetlin particle. Lazy particles, so was taken before the particles, having sort of given positions, and then the condition then is that the levels below here should interlace the level above all the time. And you can pick one of these at random, and we focus on a certain level, say P here. And the question is, so these are fixed, but these will fluctuate. So we can say that the position is denoted by G of P here. So we want to study then under this measure how this behaves, how it fluctuates. So we discussed this last time, and we saw that this is the determinant of point process. There was a formula for the kernel in terms of the double contour integral. And what I discussed there was that how you can take at least one type of limit of that formula. So the general picture, so I will not really assume that, so we have sort of point AIN, so you think of n as large, of course, but not necessarily going to infinity. But it's also, you can of course consider the situation where we look at some sequence of these such that this converges weakly to some probability measure mu. We can always think of it as fitting in a compact interval, right? Just by the scale. And then a possible picture that you can have, if you think about it as a kind of limit situation, is that in the end you get a limit shape. So there is some density here, but then you could have a sort of like a straight line here, and then something curved below that. And depending on where you are at different levels, so now this is, of course, of size n, right? So you could be a proportional to n down, but it could also be that's not necessary. I mean, you could look at levels which are sort of going to infinity here, but are still sort of not at the proportional to n here, right? But then what I claimed is that you can get different type of regimes here, different type of asymptotic behavior. So what I discussed sort of belongs to this, where you should, in terms of the limit shape, you can think of it as happening when you have this straight line here. So this was the generalized or the Gaussian regime. There is also a case here, sort of one which you can call the bounded regime, where you actually is at a finite distance, which I did not discuss, but which we have also analyzed. Then there is sort of a kind of critical level here when you have a situation like this. And when you approach this, you can have sort of basically two cases, and which I will discuss a bit more today, which because of the bias price, this is sort of the third case, this was the second case. Right? And here you have something called generalized DVP, right? A shear regime. So this is the fourth case. And when you're really here in the curved region, but not actually at the bottom, there is sort of the area case, which is more well known perhaps, which is sort of the fifth case. And what we saw, what I argued for, I mean, of course, I didn't prove that in this sort of Gaussian regime, if you scale things properly, you get a limiting kernel that which has this form. This is something in the second and SNT or the sort of rescale band positions here. Right? So it has this form. And I have a double contour interval here with appropriate contours. And then we have some Gaussian factors here. And then the aim that I explained last time is that you can in this original kernel, we had this product structure, right? We had a factor in this. Like this, so you have a sort of an actual product structure initially, and we sort of in a sense feed aspects of this product structure. You get potential infinite product here, like this. Or some asymptotic parameters. They come out of these AIs, but it's not that B1, for example, depends only on A1. Each of them depends on the whole configuration. So you can think of this, we could say, although, let's say AI is an outlier if this BI is less than infinity. So these P's here, they form an increasing sequence, but they could go up, could be infinity. So if it's infinity, the factor, of course, disappears and there is no effect of it. So we say that if it's finite here, we could say that this A1, for example, this B1 is finite, is an outlier. And in this case, it was an aspect in the Gaussian case that at least B1 is finite. So this is at least one outlier. A priori, it's actually not so clear whether, I mean, if you just given a sequence and a level, will this be an outlier? If I go sufficiently far down here, I get the area, right? So here there will be no outlier effect. So of course it depends on where you are, whether a certain has an outlier effect or not, this point. So it's something which depends on where you are and also on the whole sort of configuration. So what I said yesterday, last time, today, was also that what we're actually proving is not just a limiting statement here about kernels, but actually sort of a more precise result. So that F2 of SA, that is the sort of the right mode, the distribution of the right mode in the point process with kernel K2. So this will have a right mode point, and you can look at what's the distribution. Complete analogy with the Tracy-Widden distribution. Right? So this is sort of, in this regime, this is the analog of the Tracy-Widden distribution. So it's given by a Fredholm determinant involving this kernel. And of course, what we're aiming at is that this, in a appropriate limit, then should converge to it. But we can make this a bit more precise then, right? So this is sort of a theory now in this Gaussian regime, right? So you should, okay, say we have these points, right? And then what I also said last time is that you can parameterize sort of, even before the limit in a sense, you parameterize the position of the last particles here in terms of certain functions, which come from the fact that the saddle point is a double critical point. This leads to certain equations which involve this. The crucial function was this one, and here is the sign mistake I had was that I had said minus a. But this is sort of the crucial function, and what we had sort of the level here, P there, to be expressed. So given a certain value of zeta, which you think of as a parameter, sort of parameterizing this, I get a certain level, right? And this level has then given in terms of these functions. So as I vary Z, I can vary the level. I also have sort of an asymptotic position, which I'm sort of looking around here, right? Which is good. So this, where this is also been decided by my choice of theta. So I take some theta, there will be corresponding positions and level here, and this is given by this form. So then, and then we had certain assumptions here. Right? So I take some say in this interval minus infinity to a1, which gives, and that gives me these two, where I am. And then we have some assumptions then. And we take this a1 and you subtract off this theta, you multiply by this theta. So one of the conditions I used last time when I sort of argued that this was the limit was that this goes to infinity in that case. So, but a more precise version would say, okay, this is, think of delta something small, and this is sufficiently large in terms of this quantity delta. The other condition was that, and this is how the eyes emerged then in its argument, which I sketched then, is that you have a certain rescaling, which in this case is given by the derivative at this point. So as I said, in this case, I mean, this is a sum of n terms, so this is like a square root of n times rescaling. At least if we have, it depends of course on the detail and exactly where you are, but this is how you can think about it. And these are given, I assume that this is smaller. What I said was that this converges to this, but okay, I assume that it's sufficiently small in this terms of this delta. And this happens for all these. Right? So this could be zero then, of course, right? BI could be infinity. The third condition to be was just like we had, that there should be at least one outlier. B1 should be less than B. And then something which also comes out of the argument, sort of which to make it consistent in a sense, this has to be less than or equal to 1. So that's sort of a condition of the given one. So assume that I have this. Ending fixed. It's ending fixed. So I'm not taking a limit. So there really isn't any limit shape as I drew, right? Rather, we still have really in this picture, but a very large one. And then I also, if I fix some positive L, then the claim is that if I take the probability then that the position of the leftmost point here now at this level, right? And so this is greater than or equal to gamma minus S. So we don't use the thinking about sort of the largest one, right? And then inequality between in the other direction less than or equal. So it's just sort of. But look at this probability, and then I subtract this probability that I get from this term, right? From the Fredholm determinant. And then there are constants C and M here, such that this is less than, and I should even have there also. I keep this, but I lose a bit at a sort of a logarithmic correction here. So this is true then for this I need some restriction on the size of S here. I cannot go arbitrarily far out. and this constant will depend on this. So of course you can take the limit, and I could take a sequence here where I have all of these converges, and then this would give me that this law converges to that. But here it's a more precise version that you actually can trace in terms of approximation and how this error propagates up to even the distribution function. No n. N is fixed. So you should think of n as 100 million or whatever, really huge, right? And you take some level, and then given the delta you have this, you can check also, this is not apparent immediately, but to be consistent, delta has to be less, has to be greater than 1 over e here. I could not go along this one. So this is for consistency for this to work.
But this is true for every n.
Yeah, it's true for every n. So yeah, you should think that you take n large, right? A fixed delta, and I have this level d. You can think of this as typically being, say, proportional to n, right? So I would choose delta like almost 1 over n, right? And then I would have some condition here, everything in terms of n instead. But I don't have to choose. I could choose this larger, right? So if my what it tells you then is if I don't have such a good approximation as taking delta equal to 1 over n, I would still have some error here. Right? So it's stronger in that sense. I'm not fixing delta to have a certain dependence on n. Right? Of course, you can use this now also to produce then a limit, but just by taking a sequence and assuming that all these converge. This is how I formulated last time the convergence of this. Under a certain, that these things converge, I have this limit in kernel. Okay, any questions? Yes. More questions. Okay, I will of course not be able to prove this. It's a very long proof. I will, at the end, I will comment a bit on some of the aspects of the proof. Right? But, I mean, in no details. What I want to continue with now is to say something about these other machines. General form of kernel, like, so you can try and argue as I did last time, but you would have to do a bit different scalings and a bit different details, but you can see what kind of kernel, what would be the possible limit kernels that you can have them. And the general structure is similar to this. So the general form of limit kernel is like, so it's again, I have certain, I mean, you have sort of like some angles going out from the origin with certain conditions of the angle which I want right now. It varies depending on which of these cases you are. But there are some contours here. And then what you keep this part, and then in general you could have here also sort of, you have a cubic term here. We have this, right, I'm not sure if I mean that actually that number here. No, sorry, it should be, I actually did this, no, I should have had. This stuff. And then we have some product here, right? It has this form, so this part we had before, but it could be also that the sum of 1 over bi squared is actually not convergent, and then you have to have one more factor. This is sort of the general formula. So the case we have here is actually a situation where this k here is actually 0 in the dot. There is no cubic term, but this sum of the 1 of the bi squared is actually something finite, so you could take the square outside and then you will get a term of this form. But the general structure is this form. So when I discussed here, I didn't really enter anything into the third derivative, and this is because it doesn't somehow really come in the Gaussian phase. But in a more general situation, we have to consider the third derivative of the saddle point function that we had here. So if we have this critical point, I look at the third derivative there, and let me call this kappa state here, right? So this you get everything is all the time expressed in terms of this a function that we have. That's the computation. And then we have the scaling factor, which will be different now. So now that we come now to say to this bias graph, and this is the same scaling factor we have also in this DDP regime. So here you could see that if you don't think that this is like n, this is like n to the 1 cube, which is also typical scaling we expect to see here when the sort of cubic part sort of starts to become important in some way. So let me describe this Weierstrass regime here. Delta approximation. This can also be done, but as limits. So just as before, I mean, we have some condition that how this first one behaves. But now the condition is a bit different. I take this squared and I multiply now not by a, but with the derivative of that. So we assume that this goes to infinity. And then similarly to what we had before, if I have this, but now I have a different scaling factor. So this is the scaling factor. So let me write this as this quantity that we have there, but we compare this with some possible limit here, 1 over bi, just as before. This goes to 0 and infinity. Again, I have a condition that there is at least one outlier. But note that the definition of the outlier is not the same, right? Because they have a different scaling and different conditions. Now, sort of computation again, that the cubic sum has to be finite. And we also have a condition here on how this sort of third derivative, which you think of as some kind of curvature thing. So this was, compare this with this quantity and how this compares with this sum over the cubes, 1 over the pi cubes, and this I assume also goes to 0. So these are some conditions then. So they come out if you start to argue, as I did last time. You start to try and see what can you get out of this initial formula under now and somewhat different assumptions. Then you are led to these things. Right? I mean, they look a bit, why do I assume this? But they come very naturally, as I tried to explain last time, out of the computation. If you're focused on getting these kind of canonical products expressions in the limit. So under these assumptions, then a suitably scaled kernel converges to, well, it converges, so I change this to 3 here, and I have to modify it a bit. So what happens then is that I don't get this quadratic part anymore. So I just have a linear. But to include here the W squared over 2 pi squared into the product. Because what can happen in this case, so it can happen, and we'll show some examples, that happens in this setting, and that the sum of one of the pi squares, I assume that sum of a cube is finite, but this could actually be infinite. But what that means is that you cannot really, I cannot take this out of the product. So I cannot sort of write it in the form we had previously, where I had a Gaussian factor outside. It has to be incorporated in the sum. So this is, of course, very, I mean, it's a rather subtle difference here between the two cases, one we had before and this one. But there is a difference, and it also is not just the difference in, because, of course, it could happen that there are only finitely many bi's or less than infinity. Then, of course, this is finite, I can't take it out. Then it looks exactly like what we had before. It's the same limiting kernel, but it's not the same kind of limit, right? Because we have different assumptions, and these bi's are defined in a different way. So even though the limit could potentially have the same form in the Gaussian case, the way the limit is taken is different. Right? So it is a new situation in that sense.
So what do you mean when you say that there are how many of these are the same in the Gaussian case? Don't you have the cubes down there and no cubes up? The zeta alpha z cubes and zeta.
No, there are no cubes. In this case, in the general case, so in this case, so this capital K here is 0 in the Bayes graph. Yeah.
Kernel is still, I mean, like, is this going to be a, what is the scaling exponent here? Is it 1/2 or 1/3?
It's 1/3.
Because of,
but or you shouldn't think that it's n to the 1/3. This would depend how things, where this occurs and how things would depend on the model. Right? I will give an example here, right? But it could be n to the 1, but it could also be another power.
Right, depending on how your A scales.
Yeah, depending on everything here, right? I mean, because it depends not only, it depends on how the points behave. Let's give an example. This. That shows that this can actually occur. It's not a priori, you don't know, right? So let me not write down, sorry.
Guaranteed be able to find the BI.
No, actually, so the full picture is sort of this one, that you're looking, I mean, I've written sort of, I wrote for the second regime, you can write for the bounded situation, you can write conditions for being in this BBB situation, and you can write conditions from for being in the area case and for being at the bottom. And these are mutually exclusive and cover all possibilities. So you have, in that sense, if you have a limit, you have to end up in one of these cases. So in that sense, it is a complete classification. The only thing we have not sort of looked at in detail is what can happen at the bottom, and there are also many things can happen. But then you have to be at the very bottom. So in that sense, you have to end up in one of these situations. But it sort of, if you give me a level, I would have to compute those things and see into which case it would fit. And of course, in terms of this approximately, if I write the delta, of course, at the final case, none of them necessarily have to be good. Right? That could have something strange. But if you are close with some delta measures, with some parameter delta, then again you are close to one. So let me not write down conditions. You can write down conditions to be in this BBB situation also, right? So recall we have sort of this picture here where we have this sort of critical level, and there you could also have this BBB. So this is sort of, let me just write it here. Then actually you do have this. That's the difference. That this you have the third, I guess. You do have a cubic. It's actually given by, so this quotient would have some limit, and then the difference between this limit and this sum here would give me this k, which in that case is not 0. So this would be sort of this is the or generalized BBP situation. So a classical Python-Roche-Cauchy or BBP kernel comes from having a sort of a finite product here, but you can generalize it to having an infinite product. And somehow when you enter into the area situation, what happens then is that there are no outliers. So then this thing disappears and you get the cubic thing and you get the traceability. So these sort of are the possibilities that you can have. And of course you can ask, can you actually, I mean, we actually see them. So this bias plus thing is a bit mysterious, right? So let me sort of give you an example where you can see.
These are solved from the VAs and everything is very perfect. You get the bar stress.
Yeah, you have.
And generically you get the stuff like kind of.
It's delicate, of course. Just like in a sense, the BBP is also delicate, right? I mean it's typically you will not maybe it's, but it depends on somehow. I mean, what these conditions say. So the picture, I mean, if you don't before the limit is somehow like, I mean, you start at some points, and then it looks more much like paths here, right? When you go in, right? But at some point, I mean, when they can sort of meet here at this here and sort of be integrated into the bulk of all the rest, right? And what it depends quite sensitive on exactly where you place yourself here. And how they come together here, which depends on how they were configured here, of course, in comparison with all the other sources. So in that sense, of course, it's sensitive in the sense that it's something that happens right when you are here. But I'll write an example. You see, it's not that we have to really fine-tune a parameter. So I make it short. I take AI is I over n to some power mu. And then you can start to look at this, and I will not, and you take this mu to be between 1/3 and a half. And then you can, so I won't do the computation, so you start to look at all these quantities. But you can see that you can take this actually to be at 0 in this case. It's good enough for 7 points. And then you get, if you do this, you will end up at the sort of at the critical position here now. And this, so let me write something. Asymptotically, this is 1 over 2 minus mu, 1 minus mu squared times m if mu is between 1/3 and a half. B is the level. Yeah. So I'm sort of in this picture here now. So now I've given a certain sequence of points here. And I look at sort of at the critical or very close to the critical level. Exactly 1/2, then you have divided by log n. So this is an example. You see, this critical point need not be proportional. Right? It could be that it actually disappears. You wouldn't really see it in this kind of limiting picture. So there is, you don't really, in the limit, you don't see this straight line. This can happen. And then if you can compute then what these BIs will be, and they will be so they are all finite. You really get this infinite Weierstrass formula. You can see that sum over 1 over BI squared is actually divergent in this case. So you really need this full. So in this case, you can verify all these conditions I have in the Weierstrass sheet, but this is the situation. So this is and those infinity of the probability that the leftmost particle is greater than some gamma n which you can compute and some scaling factor which you also can compute, of course, is given by the sort of Tracy-William corresponding to the Weierstrass. And if you want to think in terms of scaling exponents, you can see this so if you take this quantity then, so this is sort of where it's supposed to be. This is sort of what you scale around. So if you divide by that and multiply that, this has order n, right? And if you compute that, so the fluctuations are of order than n to the mu. So even though I wrote this 1/3, you shouldn't think that it's necessarily n to the 1/3 because it depends on the properties of all these sums that you get, how they behave. But you can see that it somehow interpolates between the half we sort of typically think we would see anyway in the Gaussian case to the 1/3 when we go into the, because when you can check also that when mu is less than or equal to 1/3, you get not BBP here, but you get that into the air. And actually, you can prove that you can get all these cases by appropriately modifying examples like this. You can show that So it's not, even though in one particular situation you may not see all of them, you can see by modifying things you can. So I don't, for your question, I don't know, there is really no fine tuning in any sense, right? But it's rather how these quantities behave, like, at a certain level.
Then I have another question on that.
Sure.
Do you know how the curve? So you have the top of the paths that are working their way to that point, the wire stress point. Do you know how they meet it? Like, are they curved when they meet it? Are they straight lines? Do they have some like exotic some U power when they meet it? Because beyond that point, the tangency point, they'll be kind of curved, like they'll be convex. I think strictly convex. But before that, they'll be.
That this is strictly convex. I don't have an immediate. That's a good question. I would have to think. We do have sort of the multi-level thing here also, so you can see how things change as you move at a certain scale there, which may be the correct way of thinking. I don't know. One has to think. You can probably figure that out, but I don't know on the top of my head. It somehow depends on this. I introduced this function, which came from the third derivative, and some combination of these you can think of as a kind of curvature measure. Right? But exactly how that behaves there, I'm not sure. Yeah. Let me make some comments here now. So I didn't say anything. So all of these results like this are based that in all these regimes you have analog of this finite end result. So how do you prove this? Well, the proof is you start like I started. You sort of expand in some sense around a critical point. Then you also have to, of course, figure out, you have some local contours, but you also have some global contours. Right? And how you choose them is quite a delicate matter. So there are two aspects which are, if you want to really carry the whole thing out, are complicated. You have to trace this error that I have through these computations in a very precise way, all the way to the Fredholm determinant. The other thing is you have to choose the contours so they work. You know, if you think about steepest descent contours, they will of course depend on the AIs. So if I start to vary the AIs, they will change that. And it's not so easy to follow how they actually behave. And I mean, we also have this thing in this double contour integral term, so I don't want the contour here to be too close to that one. So when I start to vary, how will they actually behave? This is a bit tricky. We tried initially to use with Elno, that as I said before is the main person, to use steepest descent contours, but it's complicated. So we ended up using not steepest descent, but you choose appropriate descent contours in an explicit way, which actually work uniformly in the AI. So you make sort of an ansatz in terms of polar coordinates and verify that certain properties do hold, so that you can use that. So that's a difficult aspect, as always, in this Accelerator point argument. So, and then on top of that, you also, I mean, this is a Fredholm determinant, and so you have a Fredholm determinant converging to Fredholm determinant. To control that convergence, you also need some decay estimates of the finite end kernel as you move away here from the boundary. So this you also have to prove. And this is responsible for this extra log factor we had in the error, that you need to go a certain distance away there. So I won't really say anything about the proof. It follows a standard form that you would expect in an argument like this, but there are many, many details that you have to be careful with in this argument. So let me say a bit more about the limit shape here also. So that is not really about the limit shape. you have some, we're really looking at the final picture and it's two layers around the appropriate point at each level. But you can, of course, try to analyze the limit shape also. Even though, I mean, you could have these regimes without really having a limit shape, as I indicated here. Or a straight line. You have a limit shape, but it's all curved. So we can, of course, shift this pattern and rescale in some way. So I can say that the first particle is at some point A for all n. I don't move it from the yeah. So this is fixed. And then I have another condition, which is that what I have written before, that you have this converges to some weakly, to some probability measure. The same goes to P. And then I don't want this to be completely, it should not be a delta match. So new non-regenerate. And then in analogy, I mean, we have this function A of T all the time, but actually we used it in the argument for the finite end of the time. When you do all these arguments, you're not using the limit version, you're using the one half for a finite. But of course, there is the same rule that you have sort of the natural limit of the and then in terms of this, we can now define a limiting shape function, of a function which gives this shape. So we have a shape function, which is this one. So R is between 0 and 1. So this is sort of a coordinate going from 0 to 1. So this is the supremum as C less than, and this is the real quantity. So this is sort of what we had when we had this sort of position function before. And then you can prove a theorem then under this condition, 1 over n, and I looked at what's the position of this, right? I looked at r times n, that's how far I went down, right? Divide by n. So this should go to this asymptotic position. So this should be the curve giving limit. So this is true then as n goes to infinity in probability. So this is the shape theory, which sort of, so if you can prove that if you have these situations, then you actually do convert to shape. That doesn't, but you have to be careful here, as I indicated a bit, that you should not be too focused on the existence, say, of a straight line there in order to see different behaviors and an area. The limit shape is not the full story. But what can happen here, I mean, where does the straight line come from anyway here? Right? So it comes as follows, that if you, when I move, see, you should think of this as we move the critical point before. So I move this from minus infinity, I'm at the bottom here, and then I follow a strictly convex curve. But then when I hit A0, I'm actually not at the top here. So actually, you hit the value A, capital A of A0 here, and you're somewhere here, and then you actually continue with a straight line. This is how this kind of picture actually emerges. Okay, I think I'm almost done. Let me just make a few comments here at the end. So, as I said in the beginning of the first lecture also, there are many other models which have similarly looking curves. And you can expect to see these things in those models also, like, for example, the classical DVP was discovered in this complex covariance methods. So in that way, what you could certainly apply with some modifications these arguments to these other cases. So another instance is in gas passage percolation, where you have this Schur measure with parameters. You could also see these things. And also that's a bit more general, because for those of you who know, there are sort of two products, not just one product. So it's a bit more general in that case, when you have two sets of parameters. Right? And there is, for example, concerning GDP, there is recent journal Gelfand-Tsetlin where he studies this situation also to generalize GDP, and also says something, as I think you mentioned, about this sort of the line ensemble that you see there. So there is a lot of other work. I have not really here referred to previous work, but there are many in various type of models with a similar behavior. Many of special cases or variants of this have been looked at. I don't think this Weierstrass situation has ever appeared before. But there is a lot of work which I have not referred to. I just want to say that. So, and another way is, how should you think of these kernels? It's not, I mean, we think of the area as the universal limit. It doesn't really fit. It appears in many cases. But these kernels are also sort of limit kernels. In that sense, they are also natural kernels. So they have a very specific form. So even though they are not universal in the sense that they depend on all these parameters, you have a specific structure. So I think one should rather think of them as some kind of variation of the same thing, depending on potentially infinitely many parameters, but with a very definite structure. So not universal in the sense of the area, but still natural in some sense of a family of kernels. Okay, I'll stop there. Questions? It's a very kind of thing there that the function between support. And you could also move between different regimes, right? Given a certain initial sampling data, for example, so there are certainly many cases, and as passage population, you can also study this. So this is something that we did in a very special choice, a bit similar to this. About 20 years ago, in the context of last passage population, you can get sort of flat parts in your limit shape, for example. But by choosing things like this, it decreases in a certain way. So there are models where you can certainly have these in many different sort of type of